For this webinar today. And first of all, I would like to, our chair, Professor Salvatore Manfreda is here, so I would like to invite him to share some few words with us. Prof, the floor is yours.
Thank you so much. Just a couple of words. I would like to thank all the participants to join us today. I have to mention that this was mainly organized by a small group of young scientists that is very motivated and active in both communication and promoting these webinars that are an opportunity for all MOXXI friends, all scientists that are interested in promoting research in innovative techniques for hydrological monitoring. Today, we have the pleasure to initiate this second series of webinars with the first chair of the MOXXI working group, that is Flavia Tauro. But I have to say that I also have to thank all the other speakers that have agreed to join this initiative. And with this, I would only remind you all that we are, this community is promoting a EGO session which is already online. We will be extremely happy to have to meet in person in Vienna. Thank you.
Thank you, Prof. Okay, so before we start the webinar, I would like to share some words about our working group and some activity, what we have done in the past and what we are doing right now. So our MOXXI group is under International Association of Hydrological Science. Our mission is to promote the advancements of novel observation techniques that lead to the new source of information to help better understand the hydrological cycle. And then our working group is a friendly place to share, collect, promote, discuss, test, and improve observational technique. And then after that, I would like to share some activity that we have done. Our group already successfully organized 2 block sessions in EGU 2025. And this year, we received a lot of abstract. And then this year also, we are organizing another session. And then we will share the information about the abstract and the session in the link. And also, we already uploaded in our LinkedIn page. So you may also find there. And then we will keep updating also about the session. And another thing is that we have successfully hosted 3 webinars and another webinar which we collaborated with our MAP. And this winter edition, we also have 4 speakers. So we have our first speaker, Dr. Flavia Tauro here. And before she starts her presentation, I also like to share about her research. And so today she's going to share her research about the stage cam, monitoring water levels and catchment waterhead. So she is an associate professor from University of Tuscia, Viterbo, from Italy. She received her B.Sc and M.Sc in environmental engineering from Sapienza University in Rome. And then she also earned her Master of Engineering degree in civil engineering, civil and environmental engineering from MIT. And she graduated with Ph.D. in hydrology from Sapienza University from Rome. And also she also have a PhD in mechanical engineering from New York University Tandon School of Engineering in New York. She received a lot of awards like 2013 American Geophysical Union Horton Hydrology Award, 2014 Gruppo Italiano di Idraulica award for her doctoral thesis in water engineering, and 2019 International Union of Geodesy and Geophysics Early Career Scientist Awards. Flavia research interests include the design and the creation of innovative systems to sense the hydrological cycle. She was one of the researcher to integrate an image analysis technique with unmanned area system technology. And further, she studied a range of fully non-invasive measurement system for surface flow observation. From 2015 to 2023, she also served as a MOXXI chair for our group. So let's welcome Flavia. Thank you for joining us, Flavia. The floor is yours.
Thank you, Tai, and good morning, everyone. It's very nice to see many of the MOXXI friends here today, even if virtually. Should I share my slides?
Yes, you can share now.
Okay, let me. Just a second. No, actually, this is not the right one. So let me share it again.
Meanwhile, when you are sharing, I would like to say a few words. In this session, we are providing the certificate. So if you will receive your certificate, please find the Google form in the chat and fill your information. After the webinar, we will be sending out. Thank you.
All right, can you see my slides?
Yes, Flavia.
Okay, so do you see the presenter view or just the slide?
Now, yes, we can see the presenter view.
Okay, so maybe. Okay, I'm not sure what you're looking at now, but you should be seeing the slides. All right, so my name is Flavia Tauro, and I would like to thank Salvatore Manfreda and the MOXXI Communications team and the MOXXI Working Group for inviting me here today. So the title of my presentation is The Stage Cam Monitoring Water Levels in Catchment Headwaters, and it deals with some latest research we've been doing at the Mechanical Engineering for Hydrology laboratory at University of Tuscia. All right, let me start with a little bit of background and motivation. So I'm speaking to MOXXI friends, so we are all always investigating hydrological processes, and therefore we are always looking for data. So we need both new measurement techniques and equipment and more field measurements and monitoring. However, one of the greatest challenges we're always facing in the maintenance is the maintenance of monitoring networks, as it was highlighted in this paper by Theresa Bloom et al. In 2017. So if we look at the current status of hydrological measurement networks today, we are facing limited spatial and time coverage. The equipment that's required for monitoring hydrological processes is still pretty expensive, and maintenance costs tend to be high. So for instance, yes, can you hear me?
Yes, now we can see your presentation, but it's with the note view. Can you change, then we can see the bigger view?
Let's see.
I think now it's good.
All right.
Thank you.
Okay. So yeah, going back to what I was saying, if we are looking at the current status of the monitoring networks, we see several criticalities. For instance, here I'm reporting a graph on the status of discharge data in Germany, and we can see a sharp decline since the 1990s related to the issues I was mentioning previously. So then how do we try to improve and increase our observations of one of the most relevant phenomenon in hydrology, which is stream flow? And by stream flow, I refer to a large variety of processes that span from channel flow up to stream flow to overland flow, and with regards to this presentation today, to headwaters, so to the flow that to the surface flow that occurs in these tiny streams in the very low order catchments in natural systems. So if we look at the way stream flow is traditionally and currently measured today, we still tend to have point-wise observations at selected cross-sections, which are based on the use of measurements of sensors that need to be deployed into the flow current, so invasive equipment, which still tends to be pretty expensive, and this turns into rare measurement campaigns. So here I'm trying to outline the major issues, the major criticalities of dealing with stream flow monitoring. So when we try to observe stream flow, we are tackling a phenomenon which is highly heterogeneous and occurs at very variable spaces, very variable scales. So it includes rills, so very tiny streams, which are just a few centimeters deep, up to streams which can have very irregular beds, up to larger scale rivers with pretty large cross sections and depths. We need to capture the whole picture. So very frequently we need to have data, even if in difficult to access environments, where we need to deploy sensors and where the safety of operators may be at risk. And it is a fact that we tend to have very limited observations in case of high flow regime events, mostly related to the safety issues of operators and equipment. Third point, when we try to capture stream flow, we are dealing with a quite fastly evolving process. And here you can see, I hope you can see an example of a moderate flood event on the Tiber River, where this moderate flood occurred in the time span of a few hours. So it is very relevant to have a continuous monitoring of the phenomenon itself. A fourth issue that's related specifically to headwaters is the fact that we are dealing with a highly variable geometries of the cross sections. You can see here an example of a pressure transducer, which was installed in a headwater stream in a Mediterranean catchment close to Viterbo. And you can see that after a certain point, the transducer was completely bypassed by the flow, and the related measurements were completely unreliable and unusable for hydrological processes. So we really need to reduce the use of intrusive sensing techniques, and at the same time, what we would like to have possibly is something that allows us to monitor the status of the cross-section, even if we are not there and the cross-section is difficult to access. So most of my research in the latest years has tried to tackle this objective of stream flow observations by relying on image analysis. So by using a fully remote technique, such as the use of cameras, to capture what's going on both at the channel, at the stream, at the overland flow, and headwaters level. So we all know why images offer several advantages with respect to traditional approaches. We do not need to deploy any sensors in the flow current. We have a 2D reconstruction of reality. So we have a spatially distributed rather than point-wise measurement. We also, by simply adjusting the acquisition frequency, we can have up to potentially continuous depiction of the hydrological phenomenon. And by adjusting the spatial resolution, we can also try to observe phenomena which happens at very diverse scales, as I said, from rills up to streams and large-scale rivers. And another asset that's related to the use of cameras, which is, I think, very relevant for headwaters monitoring, is the fact that we can have a real-time inspection of the cross-sections, even in very difficult to access environments, and we can really understand what's going on, why we're getting a certain type of measurement in such complex environments. So, of course, I'm not the one who, I'm not the first who used the images for hydrology. We have to go back to the pioneering work by Fujita et al. In the 1990s. They were the first to translate this scheme that was born in fluid dynamics lab to a high-speed cross-correlation algorithm. So I'm talking about large-scale particle image velocimetry that can be applied onto real rivers. And of course, we have several papers that deal with this fact, also try to tackle this objective from aerial images. And I've done something in this respect, also developing and working on some tracking scheme, and by developing some high visibility surface tracers, let's say buoyant tracers, that were meant to highlight, to emphasize the flow and therefore to facilitate its detection. I've worked also on the entire pipeline from frame extraction to camera calibration, image ortho rectification, frame calibration, frame enhancement, up to the development of usable data. And I've tried to apply the whole process and to develop a usable procedure at very diverse scales, spanning from overland flow. So we've done some experiments on an experimental hill slope in the outdoor lab at University of Tuscia. And we've used, for instance, the high visibility tracers I was mentioning earlier, and some computer vision technique to detect the onset of overland flow. We've also developed the very first image-based permanent gauge station, so the so-called gauge cam station on the urban tract of the Tiber River, and this this allows to capture almost continuously videos of the surface of the river, and therefore to detect and develop a kinematics map of the river itself. And we've tried to reconstruct the behavior, the flow behavior for a pretty significant periods of time for the Tiber River. And of course, we've applied also these techniques and these procedures to footage collected from unmanned aerial systems. And I'm very happy we've been doing this also with many MOXXI friends. And I think many of you know already the story. So we've assessed the feasibility of using unmanned aerial systems for monitoring surface water, surface flows, and hopefully these techniques are more and more being taken up by hydrologists all over the world. As an alternative also to large-scale particle image velocimetry, we have been developing other computer vision techniques which do not rely or are not exclusively based on the use of surface tracers, and still enable a pretty accurate reconstruction of the kinematics of the flow, of the surface flow. So, building on this past work, what I'm presenting today is something a little bit different, and it's called the stage cam. It's a novel approach we've been working on in the latest years, which enables the estimation of the water stage, of the water level, in ephemeral intermittent streams, which are typical of headwaters, so of these very low order catchments of the drainage networks. And what we've been trying to do here is trying to develop an all-in-one system where we could not only capture the images, but also process them and develop and get to a measurement on the edge. So the system is fully based on images, and as you can see, it's just a box. It's, actually, you are not looking at the latest version of the box, which looks much fancier now, but we just received it yesterday, and I wasn't able to include the pictures. Anyway, it's just a simple box with a camera, a system of infrared LEDs, and all computations are performed on a Raspberry module. And we have 3 protocols for transmitting data. The system, the box is capable of developing its own Wi-Fi network, and it features also a SIM card and a LoRaWAN module. And it's also powered by a solar panel, and you are potentially able to connect to it through a monitor and a keyboard. So there are some USB ports and HDMI ports, so you can simply connect your devices to, just to look at what the system is doing, and of course to set and change any settings you'd like. So you can see a picture of the box opened here, and here is a picture of the system in place, so in an actual headwater stream, just to explain how the working principle functions. So as I said, here we are in a Mediterranean headwater. We have this very small stream, which is at the very beginning of the drainage network. On the river bank, we have this box, the stage cam box, which is looking at a target. What is the target? The target is an extremely thin metal pole, which is set into the center of this tiny stream, and it is also highly visible. Why is it highly visible? Because it's painted in a highly reflective paint, which is very nicely captured with our cameras, which features an infrared filter and LEDs, and infrared LEDs on during the image, when the image is taken. So you can see some pictures here taken during the day, in the afternoon, and at night. You can see that this feature is very nice, that enables us to keep taking measurements even at night. And here with this scheme, I'm trying to explain how we go from the images to the water stage measurement. So we take RGB images, we convert them to grayscale, and then we trim a cropped region around the target. So how can we do that? Of course, these are fixed settings that we can determine once we install and calibrate the stage cam on site when we install it for the first time. Then on this smaller region of the image, we apply some segmentation algorithm, mostly the OTSUS segmentation. And what happens is that we quantize the image, basically. So we assign different numbers to different regions just based on the intensity histogram. And we recover the region which is the brightest among all of the identified regions. Why this? Because the brightest region always pertain to the target, which is, as I said, characterized by a high visibility due to this paint. Then we simply bound the target with a box and estimate the height of the target. And we subtract this value from the actual length of the target, of course, the length which is out of the riverbed. This is a known parameter as we measure it once we install it for the first time. And by this subtraction, we get to the water stage, so the level of the water in the stream. So here I'm trying to report some of the design to device pipeline we've been following to take this very simple working principle up to a sensor. So this is the set of 3 questions we've mostly focused on. So 1, can the box be used for long-term continuous monitoring in remote areas? 2, what is the best configuration, hardware configuration for transmitting data? And 3, can we use the box for taking pictures and measurements in intense sunlight, which is one of the most challenging conditions for images? So we have tried to respond to these questions by performing several different experimental campaigns. So to assess long-term continuous monitoring, we've been installing the box in the Andes, in Peru, in a very remote area at 4,000 more meters above sea level. Very difficult to access. Second question, the transmission protocols. We've installed the box in a mountainous catchment in the Italian Alps. And third question, we've coped with intense sunlight by installing the box in the Mediterranean catchment, which is our reference experimental site and is located nearby the university in Viterbo. All right, so here you can see some results from the Andes. So we've been monitoring, we've had the box up and working and functioning for more than a few months. You can see some pictures here at night and during the day. What you can notice is that unfortunately, with the very first hardware configuration, during the day, the target was not the brightest object in the field of view. And this unfortunately resulted in the fact that we weren't able to get reliable water stage measurements during the day, while it worked pretty well at night. So we changed a little bit the hardware and moved to the Italian Alps. You can see that things improved a lot. So here are pictures at night and during the day. So the system worked pretty well, but we introduced the fisheye camera, and this made the target appear smaller and therefore more difficult to detect in some cases. So this didn't work like very well, but on the other hand, what worked well was the fact that we were able to feature to retrofit the system with the 3 different transmission protocols, data transmission protocols I told you. So the system was capable of connecting both to the internet through its SIM card and to the LoRaWAN network. And that was pretty good for sending the data directly onto our remote server. The nice thing is that this system is capable of transmitting both the raw images and the numbers, so the water stage estimation to the server. And this is very nice because by looking at the raw image, you can actually understand what's going on, and if the setup changed, if something happened, if there was some issue with the cross section, and then eventually go on site and target the issue. All right, here in test 3, you have the results for the last experimental campaign in the Mediterranean catchment, and you can see that the water stage estimations finally were pretty reliable. What we did was we again changed the optics and improved the infrared LEDs and improved also the camera filter. And this is what the target looks like during the day in a very intense sunlight conditions. So just to wrap up, as of now, the StageCam box is capable of addressing acquisitions both in intense sunlight conditions and at night, which are the 2 extremes and critical conditions for image-based hydrology, in my opinion. We've also demonstrated that long-term, pretty continuous monitoring is feasible with a sensor like this one, but we are still working on future ameliorations. We are trying to explore alternative connectivity and transmission protocols to even enable data transmission in extremely remote areas where there's no coverage for the SIM card and the LoRaWAN network is not nearby. And in addition, we're trying to include and integrate the velocimetry algorithms we've been working earlier together with the pollutant identification protocols. We've been working with Salvatore Manfreda and his group, and together with some cross-section reconstruction algorithm to give MOXXI friends, to provide MOXXI friends with an all-in-one tool for hydrological monitoring. And with this, I would like to thank our funders and especially all the people who have been working on the StageCam project. And of course, all of you for listening today.
Thank you, Flavia. It was really wonderful and very much very interesting. And we got one question, I think, regarding to the StageCam system. I think they ask which Raspberry Pi system is in it?
It's a Pi 4, Raspberry Pi 4, CM4, if I'm not mistaken.
All right, thank you. And okay, there is another question coming up. Are there any specific challenges around GDPR data? For example, we have had a lot of trouble getting approval from our in-house legal team to use camera because of concern about capturing images of people without their permission.
Thank you. So this is a very nice question, but we never had actually the chance to tackle it because really the areas, the environments we are installing the StageCam are extremely remote. So we've never captured any people passing by, so it's very unlikely that we could get some person. But definitely, I mean, if you install this in an actual river, maybe there is some privacy issues that you would need to tackle, I guess.
Okay. Thank you. And there is also another question, and it's like, what is the cost to manufacture the stage cam? And is the design available, I think, to the public? Yes.
All right, so the cost, we've been trying to keep costs extremely low. So my estimate is that, so we've been helped by a company and we don't have a precise cost estimation so far. We are working on that as well. Of course, the costs tend to decrease as we increase the number of stage cam boxes we produce, but my rough estimate is that we are around 500 euros. And the design is under review together with the software, and so all the hardware description and specifications will be available together with software and codes and everything. So we are doing everything to make it public. So it's just under review, and hopefully it will be out soon. How do I do power cycling? So,
yes.
Hi, Hessel, how are you? So we have the solar panel that charges a lithium battery and that sustains the system when there's no sunlight, and I mean, as far as I understand, it's mostly it. So we never had like huge issues related to power.
So there is also another question, like stage cam camera has much lower maintenance than the standard stage measurement, like pressure transducer.
Do you find this? So my experience with the pressure transducer was not positive, I must say, but not related to maintenance exclusively, but mostly because of its invasiveness. So as I reported in the presentation, that is an actual picture of a pressure transducer we've been trying to install in the Mediterranean catchment, in the headwaters of the Mediterranean catchment, exactly where the stage cam box was later installed, and simply didn't work because it was very soon bypassed by the flow, and the measurements it gave us were simply unreliable. Another advantage that I already remarked is the fact that with a pressure transducer, you cannot explain why you're getting some measurements, while by using the stage cam, you can actually see what's going on. Even if the measurements are not reliable, you would have the proof just by looking at the image.
All right. So what could be the next steps for the stage cam?
So as I said, I would like to even improve the data transmission protocol that facilitates a lot the usability and the uptake of the stage cam in diverse experimental campaigns. And another very nice thing that we are working to is the integration with the other algorithms, like the surface velocimetry algorithm and the cross-section reconstruction algorithm. That would be very nice to give us an all-in-one unit that is capable of giving us different parameters, not only water stage, but also velocity and potentially, of course, flow discharge, which is relatively untapped, especially in these critical environments like headwaters. So that will be our long-term goal.
Yes. Oh, I also have one question. And what could be the challenges during the severe weather condition using StageCom?
All right. What do you mean by severe weather? We had some failures, of course. There is an interesting feature of headwaters is that their hydrological response is very fast and extreme and tends to be extreme. So what happened during a high flow regime event in the aftermath of severe precipitation was that the water level increased by almost a meter, and the stage cam was completely destroyed and flushed away. So this can happen, of course. As you have seen, we have simply set it on the riverbanks soil. We don't have any fancy infrastructure to hold it in a special way. But the thing is that we want to have an instrumentation which is quite inexpensive, so we would be able to accommodate failures, basically.
Right. And there is also another question.
Would I be interested in considering AI models as part of my workflow? Yes, I think this is a quite broad and general question. In principle, yes, but I don't know if you're referring to a specific part of the workflow. Of course, we would try to minimize algorithms that are too much power expensive, just for keeping the battery and the solar panel small and easily integrated in the box.
Right. Okay. I think we still have some few minutes, but I want to say, like we would like to have a group photo together. We share also the background for this winter edition. Like if anybody would like to join, you can also use the background, and we can take the picture together. And the background is in the chat. You may find the just like us. So let me see.
If I can, I would only add a few words. First of all, it's really a pleasure to see that we reached more than 30 participants. So Flavia, the topic you discussed was is attracting and stimulating. And this is also a sign that the MOXXI community is very active, and there is a lot of interest around these topics. I really need to thank all the communication work group that is supporting this initiative. And since I have seen many scientists in the webinar that could provide eventually, that could be interested to be speakers, if there are potential candidates, don't hesitate to contact us, because this seems to be stimulating and interest initiative to promote also in the coming future.
Thank you. We have a last question. So after that, we can take the picture together. So how large is battery plus panel? And we are working with a similar box, but power cycling and doing edge velocimetry. It's require 40-watt panel plus 84-watt battery.
All right, so I can look it up because I would like to give you the exact numbers for the final configuration, but my guess is that the solar panel is a bit smaller than you have, but I will email you the correct numbers maybe later, if it's fine with you.
All right. Kim, are you taking the picture, right? Okay. So is there any issue with opening the I mean like feature to open the camera? Like please let us know, because I heard that there is some problem. They cannot open the camera. This feature is not working. Okay. I guess. All right. Okay. Kim, I think we are good. So we gonna take the picture together. Just like if you can please open the camera. All right, if everyone is
Maybe not all of them are willing to turn on the camera, but I think it's fine. I think we can wrap it up.
Kai, we cannot hear you.
I think we can wrap it up. Thanks a lot, everyone, and it has been really a pleasure. I hope to see you in the next webinar, and probably we'll meet soon in Vienna with many of you.
Thank you, everyone.
Thank you.
Bye.
Bye-bye.
Okay.